One day, a single red ember will outshine entire galaxies. That ember is a tiny star that burns almost forever. The key point up front is simple. The last stars are small red dwarfs sipping fuel. They live trillions of years while big stars die young. Tonight's sky is crowded, but their sky will be lonely. We can map that future with physics we already tested. So here is the universe when time has gone quiet. A dim red sun hangs over a frozen, airless world. That faint sun is a red dwarf, the smallest true star. It is a hydrogen burner just like our sun, but thriftier. This matters because these are the lights that outlast everything else. Their trick is simple and a bit elegant. They are fully convective, so fresh hydrogen keeps circulating into the core. They also shine weakly, so they spend energy painfully slowly. In stars, lifespan rises sharply as mass falls. A smaller mass means cooler core, lower pressure, and slower fusion. There is another player here, which is metallicity across time. Later stars can form with fewer heavy elements, which changes opacity. Lower opacity lets energy escape and lowers the core temperature. That further slows fusion and stretches a life already long. Example in real terms. A red dwarf with 1/10 solar mass glows at a few thousandths our sun. It can live around 10 trillion years, give or take. Another with 8% solar mass crawls for even longer. It barely clears 0.1% of solar luminosity. Near the end, it may heat and turn slightly bluer. The last few billion years look brighter, but not by much. Rule of thumb, smaller star means slower burn and longer life. So the picture is clear. The last stars are tiny red furnaces, burning with endless patience. Across a ghostly galaxy, long streams wrap the core like rings. Those streams are tidal scars left by a billion quiet orbits. They mark a slow wind down, not a sudden stop. The idea here is the late stelliferous era, the star-making tale. It matters because it sets when skies finally go dark. How does star-making end inside a galaxy like ours? Gas is recycled by dying stars, but much gets heated or ejected. Supernovae and black hole outflows kick fuel out past the halo. Fresh inflow dwindles as the universe expands and filaments thin. The reservoir runs dry and clouds stop collapsing into newborn suns. Meanwhile, dark energy stretches space and isolates the local group. Distant galaxies slip beyond our cosmic event horizon, forever unreachable. Inside the island, mergers continue and fuel gets used up. The net result is a slow fade in starbirth, then silence. Example in real terms. Many models put star formation near zero around 100 trillion years. A red dwarf born near that sunset might shine 10 trillion more. Long after the factories close, some lanterns still hang on. One sentence recap. After a long decline, fuel is gone and starlight keeps shrinking. Far beyond, faint filaments fade like spider silk in moonlight. This is the Degenerate Era, when remnants rule the night. That phrase means white dwarfs, brown dwarfs, and sleeping neutron stars. It matters because light gives way to ash and quiet embers. What happens is patient cooling, driven by radiation and neutrinos. White dwarfs shed heat for eons and slowly crystallize inside. Their cores form lattices, like a diamond planet the size of Earth. Brown dwarfs radiate away their last stored warmth into blackness. Neutron stars keep their magnetic scars, but shine only in ghosts. Collisions can still happen when orbits drift after many encounters. Two brown dwarfs may merge and briefly ignite thin hydrogen shells. A dying red dwarf can heat up and turn slightly bluer. That short blue phase ends fast and the light sinks red. Example with a number. Cooling below 1000 Kelvin can take more than 10 to the power of 15 years. A typical remnant system survives countless orbits across quadrillions of years. Rare sparks appear, but they do not reset the clock. Bottom line, remnants fill space and light loses its throne. You flip through a ledger of time, etched with absurd numbers. That ledger is our forecast, built from tested physics and models. It matters because numbers anchor pictures when wonder runs wild. Each timescale flows from mass, temperature, and quantum rules. Gravity sets orbits, fusion sets lives, and radiation sets cooling. The stelliferous era fades around 10 to the power of 14 years. The longest-lived red dwarfs survive near 10 to the power of 13 years. Typical white dwarfs cool below orange glow after 10 to the power of 15 years. Some theories allow proton decay only beyond 10 to the power of 34 years. Giant black holes evaporate over staggering times. Think between 10 to the power of 67 and 10 to the power of 100 years. The de Sitter horizon sits near 10 to the power of -30 Kelvin. One sentence recap. The scale of the future is not centuries, but exponents. Shards of worlds drift past dead suns like ash on cold wind. Another lever might exist, hidden inside every proton in space. That lever is proton decay, a slow unmaking of matter. It matters because it would erase remnants long before black holes end. The idea is simple, if exotic, and still unconfirmed. Protons might turn into lighter particles by rare quantum processes. Those decays would spit out positrons, neutrinos, and faint gamma rays. Over time, solid matter would crumble into radiation and dust. The rate is unknown, but there is a solid floor. Experiments push the half-life beyond 10 to the power of 34 years. Many theories allow far longer, beyond 10 to the power of 36. What would that do to a cold white dwarf nearby? Its atoms would slowly vanish and its mass would bleed away. The star would fade faster because the lattice keeps losing protons. A planet around it would erode, grain by grain, into light. Example with a number. A remnant could dissolve by around 10 to the power of 40 years. That number depends on the true lifetime, which we still chase. Net result, proton decay would clean the stage early, if nature allows it. A silent halo glows faintly around a lonely galactic core. Suppose protons are stable, and matter cannot shortcut into light. That choice matters, because gravity still sculpts a very long story. The working parts are orbits, encounters, and tiny gravitational tugs. Over time, encounters exchange energy and sling bodies into intergalactic dark. Bound systems slowly evaporate, one remnant at a time, to infinity. Black holes dominate the centers and swallow what wanders near them. Some remnants get ejected and drift alone for quadrillions of years. Two body relaxation times can reach 10 to the power of 19 years. Central stars and remnants get eaten first, near dense inner regions. Outer bodies escape earlier, pushed by subtle nudges each passage. Collisions do happen, but are vanishingly rare after starbirth ends. Example with a number. A cluster can lose most members within 10 to the power of 15 years. A galaxy remnant thins dramatically by 10 to the power of 19. Rule of thumb, gravity frees the outskirts first and the core last. So the picture is inexorable. Gravity either ejects the quiet ones or feeds the dark center. Close to the dark heart, spacetime bends like glass warmed over fire. Here the last engines run, the black holes we already see today. Hawking radiation is their leak, tiny and incredibly slow at first. That phrase means black holes glow because quantum fields near horizons flicker. It matters because this leak is the final drain of structure. How does the glow work in one clean sketch? Virtual particle pairs appear and one falls while one escapes outward. The hole loses mass and the glow grows warmer each year. Smaller holes radiate faster and large holes are freezer cold. Rule of thumb, bigger hole lives longer and shines fainter. Example with numbers that anchor the endgame. A 1 solar mass hole lasts about 10 to the power of 67 years. A billion solar mass giant lingers near 10 to the power of 99. The last moments end hot, with a final burst of high-energy light. Before that, the universe is filled with a thin bath of photons. That bath carries almost no structure and almost no memory. Bottom line, Hawking glow takes everything apart, given unthinkable time. The web itself goes dim, until only horizon haze whispers back. That haze is De Sitter warmth, the floor set by dark energy. It matters because there is no colder destination beyond that floor. Everything smooths out and all gradients flatten to quiet equilibrium. The sky still glows faintly because horizons have a tiny temperature. That glow is around 10 to the power of minus 30 Kelvin. No engine can run on that and no chemistry can chatter. The last sparks already died or were swallowed by black holes. What remains is radiation, neutrinos, and perhaps lone electrons drifting. We end where we started, with a single red ember remembered. After the last star, the universe keeps time but forgets detail. If that picture stuck, tell me what future scene you saw. That tiny red ember will outlast galaxies, then fade into memory. We just walked its timeline from crowded skies to horizon haze. The picture is simple and heavy with time. Small stars sip fuel, black holes leak, and structure unwinds. If this helped you see that far future clearly, stay curious. Subscribe for more deep time stories told calmly and cleanly. Thanks for watching Under a Very Young Universe.